Thank you for the kind introduction, and thank you for coming to my talk, and thank you for making the earlier time, and I'm glad it worked out so well that a lot of you were able to make it. Before I start, I have to apologize that I probably have to cough quite a bit, especially during the first 5 minutes. I was down with quite a heavy chest infection. But I didn't want to postpone my talk because I've got quite a hard deadline to work towards too. As you can see, there's not much of a delay in this. So the title of my talk is How Machines Learn to Talk. And what I'm reviewing today are so-called machine learning techniques to build conversational AI systems. So I will explain to you some of the advantages and some of the drawbacks of these techniques during my talk. So the dream or the desire to talk to machines is actually as old as the Industrial Revolution. So back then, people made these sort of bizarre-looking instruments to mainly figure out the hardware, how we can get sounds out of machines. So nowadays, we pretty much solved the hardware problem, and we moved on to so-called conversational agents. So these conversational agents can have different forms of embodiment. So for example, the first one here, that's the sign for Siri. And Siri is a conversational agent which can either live on your Macintosh computer or on your Apple iPhone or on your Apple Watch. Then you have the so-called smart speakers here. So that's Amazon Alexa, and that's Google Home. And then you've got chatbots, which are mainly text-based. So they live on different messenger platforms, such as Slack, Telegram, or Facebook. And then you've got these humanoid robots, such as Pepper, which you've seen, which you hopefully saw when you entered the lecture theater. So industry is really excited about these conversational interfaces. And when you look into the market forecast for AI, they actually rank third in terms of the predicted growth rate over the next couple of years, just after autonomous robots. And they're also, interestingly enough, they rank before neural networks. So neural networks is a machine learning techniques, also called deep learning, which has advanced the field of AI over the last couple of years quite tremendously and has caused a lot of excitement in our community. And I will come back to this later in my talk. Excuse me. So why are these voice assistants actually useful? So according to Microsoft CEO Nadella, he says, bots are the new apps because they fundamentally revolutionize how computing is experienced by everybody. So what he actually means by that is, usually if you want to find a piece of information on your smartphone, for example, you take out your phone, you think about which app to use. You look for the app, you open the app, you try to understand how the app works, and then eventually you might get that piece of information, right? So what these voice interfaces are supposed to do for you is that they give you a unified way of accessing this information by directly talking naturally to your phone or to your voice assistants. And then, at least in theory, you should be able to get that piece of information you were looking for. So in my research, I'm especially interested how we can use machine learning for building these conversational systems automatically. So traditionally, these systems are built using handcrafted rules. So a system designer, software engineer would sit down and write a lot of rules, how these systems are supposed to behave. So now when you move to bigger domains, obviously these rules will become more complex. And then every time you build a new system, you have to start from scratch. So the idea of machine learning really is that these systems can learn by themselves by basically reading a lot of data and then processing statistical patterns in this data and memorizing these patterns. So that's machine learning in a nutshell for you. So that's how these systems are really supposed to gain their knowledge by themselves. So the questions I've been exploring regarding machine learning are which machine learning methods are actually suitable for building these conversational systems, and will future machines actually speak neuralese? So I've already mentioned these deep neural networks, as we call them. So will these methods also be successful for conversational systems? And can we use machine learning for customer-facing applications where you obviously have harder constraints on what the system is allowed to do and what it should be doing? And then finally, what do we actually learn when we learn from big data? So these are some of the questions I hope to answer during my talk. So to give you a rough overview what to expect, I will start by reviewing these so-called task-driven systems. So these are transactional systems where you collaborate with a virtual agent to solve a task. So for example, if you do online banking or if you search for a restaurant, these are all task-based systems. Then I will be moving on to so-called social chatbots. So these are chatbots which in theory should be able to talk about anything. So we call this open domain. And this is a very challenging problem, as you can imagine. And they should also be able to do that in an engaging way. And then finally, I will talk about future challenges in my research. So, regarding the task-based systems, they usually follow a standard architecture. So you start with the user saying something. So out of his mouth come waveforms. And these waveforms then get recognized by the speech recognizer and transformed into a string of words. And then these words need to be made sense of. So some sort of understanding what these words actually mean. And we call that a semantic parser. And in our case, what the semantic parser does, it transforms an utterance into a meaning representation. And in this case, we call this a dialogue act. So the user says, I'm looking for a cheap restaurant, and the meaning representation is very simple. It just says something like the user is informing the system that the price equals cheap. And then this dialogue act is fed into what we call the dialogue manager. So this is sort of like the brain of the system, which tries to make sense what's going on and tries to come up with a good reply strategy. And it usually also has access to some sort of back-end database, like a knowledge base. So in this case, the dialogue manager just says, well, present all the restaurants where the price equals cheap. So again, we're on this abstract dialogue act level. And then these dialogue acts need to be transformed, translated back into human language using words through the natural language generation module. And then finally, we need to synthesize these words into speech waves, sound waves again, by the text-to-speech synthesizer. So I've mainly been working on the dialogue manager. I've done a lot of work recently on natural language generation. And I've also done some work on the text-to-speech synthesis. So mainly, as you can see, the output side of things. So I already mentioned that traditionally these systems were mainly hand-coded. So the system designer would come up with some sort of decision tree of how the system should behave in a situation, and then transform this decision tree into a set of rules. And I've already mentioned that this is not really scalable, and especially when we move to domains which we call open domains, so domains which are not restricted to a certain task, it gets pretty much impossible to write down all the rules. So this is why people have turned to machine learning, and one of the early machine learning techniques people used was called, or is called, reinforcement learning. And it's a technique coming from robotics. So the idea is that you've got your agent, so your system here, and the system can take a predefined set of actions. So in our case, anything the system might say. And it then will observe how these actions changes the state of the environment. So in our case, how will the user react if I say something? And it observes that reaction, and it also gets a reward of how good or how bad this new state is. And according to this observation, it updates a value function. So this defines a value for each state and each action. And if you do this often enough, you basically end up with a big lookup table of which action is best to take in each state. So this framework is quite attractive from a theoretical point of view because it sort of mimics what we think animals do and what to some extent also humans do. So it's some sort of trial and error learning where the system basically goes off and learns by itself through interaction. Now the problem is that the difference between a machine and a human is that children, for example, learn by what we call one-shot learning. So they observe something once and they immediately grasp it and learn from it. Whereas machines need to see many, many examples of the same instance until they actually discover a statistical pattern. So one of the problems is that these systems using reinforcement learning just need a lot of training episodes, and which means that you either need to have a very patient user or you resort to something which we call simulated users. Other problems with reinforcement learning is that you have to manually specify the learning problem, meaning that you have to design the reward function, you have to design the state space, you have to design the action space, and you usually also handcraft the outputs, which can occasionally mean that the system actually thinks it said something which it didn't say. And obviously this mismatch is quite a problem for systems to have. So very recently, about 3 years ago now, people started to replace this traditional architecture with a new architecture which we call end-to-end response generation. And here the idea is actually really simple. So in case, instead of having this modularized architecture, we just map all the user input in terms of the words of the user to an output in terms of a string of words. So we directly map user input to system output. And we totally get rid of this abstract meaning representation in terms of dialogue acts. So the big advantage of getting rid of dialogue acts is basically that we can now learn from raw data. So anything which is a conversation out there, we can learn from. So we can use Twitter data, we can use subtitles, we can learn pretty much from any data set without having to annotate it. So that's one of the big advantages of this new framework. So the way this is implemented is via neural network. I've already mentioned that. And one standard architecture for neural networks is what we call a sequence-to-sequence model. So the idea is pretty simple. You start with an encoder which encodes every word in the user utterance, and this LSTM stands for long-term short-term memory. And then it feeds that into a decoder, which again is a long-term short-term memory, and that then decodes the system utterance word by word. And it does that by learning the frequencies from a very large data set. So we wanted to know how good are these methods really for building conversational agents. And the first question was, how good are they for task-based systems? So in order to answer this question, we wanted to do it really thoroughly. So we did something quite large scale. So we organized a shared challenge. So we called it the End-to-End Natural Language Generation Challenge. And a shared challenge in our field pretty much gets organized by you collect an interesting data set, so something which you think will be picked up by the community. And then you release that data set to the research community, and you hope that people are working on this data set and then submit their results for you to evaluate. And then in the end, you've got this opportunity to compare a lot of different system architectures with each other, and you hopefully learn something about which system is good for this task and which system isn't that good for this task. So this is what we did. So we collected a large data set about people talking about restaurants. So for some reason, restaurants are very popular in our research community. So that's why we chose this domain. And indeed, it was very popular. So we received a total number of 62 system submissions, which was way beyond what we were hoping for. And all these systems had quite diverse architectures. And these were submitted by 17 institutions from 11 countries, and about a third of these submissions coming from industry. So we consider this unexpected success as a confirmation that this is a very timely task a lot of people are interested in. So, as I said, this gave us the opportunity to really compare different system architectures with each other. And one model a lot of systems implemented was this aforementioned sequence-to-sequence model. And then another large group of people stuck to hand-engineered systems, so more traditional hand-engineered systems. And by comparing these two sets of system architectures, we were able to make general conclusions. So for example, we found that these neural methods were very good in producing natural sounding output. However, they were less good in producing output which was reasonably complex or of sufficient length, or it also wasn't very diverse. And they often miss out on information. So meaning, for example, they just won't tell you that a restaurant is child-friendly or that it serves Chinese cuisine, which is information you really need. So this is not a good thing if the system withholds that information. And they're also scored slightly lower in the overall quality ratings by the user. So the reason for this is that these neural systems, what they do is they tend to settle for the most frequent option. So by learning from these data sets, they extract frequencies and they penalize length in favoring high-frequency word sequences. So for example, if you've got a large data set and the users very often says things like, I don't know, or or okay, then your system will learn just to say these very boring, repetitive things without actually giving you much information. So that's not much you can control with these neural methods. So what we tried next was an even more challenging problem, namely social chatbots. So I already mentioned this is open domain conversation. So this is similar to a human conversation where you can expect to quickly switch between all sorts of different topics. One moment you talk about politics, then you talk about sports, and then you discuss what your plans are for the weekend. And that all should be covered by a system, and it should also entertain you by talking about all these different topics. So we call this actually an AI complete problem. So there are very few AI complete problems, and this is one of them. And so this is one of the holy grails of AI. So if you solve that, you'll be famous. So nevertheless, we tried to solve it. And again, we don't like to do things small scale, so we did it large scale by entering the Amazon Alexa challenge. So the Amazon Alexa Challenge was inaugurated in 2016, and we were one of the first teams to enter. And the challenge was to build one of these open domain social bots, and also to actually make a social bot which was really engaging for the user, so something fun to interact with. So something which would actually keep Amazon customers entertained, right? And our bot was then evaluated by real Amazon customers, so it was released all over the US, and real customers interacted with our bot and also gave us scores how good or how bad they thought our bot would be. So we were not the only people entering this challenge. Indeed, we were in quite distinguished company. So we competed against the University of Berkeley, Santa Cruz, Edinburgh, Carnegie Mellon, Montreal, Trento, Washington, Princeton. So all the big names are there, and of course, Harriet Watt is one of them. So we were very hopeful that this time, actually, these neural methods would deliver what we hoped they would deliver. And we were very much inspired by a video which went viral in 2011, which advertised a machine learning-based system called Cleverbot. So according to the developers, this was purely trained on data, on customer interactions. And I just play you the video to get an impression of what might be possible. Sorry, let me just see.
Hello there.
Hi.
How are you?
Great, you.
I'm okay.
That's good.
Are you good?
Yes, I am good. I just said I was.
No, you didn't. I said I was.
So you are a robot?
No, my name is Cleverbot.
Yes, you are a robot and your name is Cleverbot.
I am a robot.
Yes, I know.
Together we are robots.
I'm not a robot. I'm a unicorn.
But you said earlier that you were a robot.
I did not.
I thought you did.
You were mistaken. Which is odd, since memory shouldn't be a problem for you.
I've answered all your questions.
No, you haven't.
What is God to you?
Not everything.
Not everything could also be something. For example, not everything could be half of something, which is still something, and therefore not nothing.
Very true.
I would like to imagine it is.
Do you believe in God?
Yes, I do.
So you're Christian?
No, I am not.
But you say you are not helpful, therefore you're a meaning.
How you say idioty.
That does not make sense.
Don't you want to have a body?
Sure.
Or if what?
Right. So, as you can imagine, we were very impressed by, after watching this video. And this is the system talking to itself, by the way. So we were hoping to do the same for our Alexa challenge. So what we did, we implemented a neural model and we trained it on a really big data set. So we got data from Reddit, we got data from Twitter, we got movie subtitles, we got daytime TV transcripts, and we threw that all onto our neural model and we trained it. However, the results were slightly disappointing. Either it produced really boring answers such as, I don't know, yes, no, maybe, okay. So this is, again, as I mentioned earlier, to that these models favor high-frequency utterances in the corpus, or it produced utterances which were highly inappropriate. So just to give you an idea what I mean by inappropriate. So once our system said, I can sleep with as many people as I want to. And I just want to draw your attention to the fact that this is really hard to filter for profanity. So we did apply profanity filters on our data, but what would you want to filter for here? Because the phrase sleep with could also be used in different contexts, like I like to sleep with my window open, or my daughter likes to sleep with her teddy bear, things like that. Then our system said things like, you will die. It probably learned that from the movies. Some users actually asked, shall I kill myself? I hope that was just a rhetorical question. And our system said, yes. And one user asked our system, shall I sell my stocks and shares? And our system said, sell, sell, sell. So as you can see, this answer is actually contextually very appropriate, and we were really happy with it. However, Amazon wasn't happy about our system giving financial advice at all, and told us to quickly fix that. So we decided on a different type of architecture, where we basically imposed a set of rules covering these crucial situations. And then for all the other situations, we implemented a set of specialized bots. So for example, we gave our system a persona. We had a bot covering all the recent news. We had a bot knowing a lot of interesting facts. We had a bot which read all of Wikipedia. So these, these bots were mainly based on machine learning techniques. And then once a user utterance comes in, each of these bots would actually post a possible reply. And then we trained a neural ranker to evaluate which reply is actually the best in a certain context. So this neural ranker was trained on actual customer ratings. So as I already mentioned, these systems were live, and they were rated by real Amazon customers. So they would rate our system on a scale from 1 to 5, and we used these ratings to train our ranker. So as you can see, so this is the user scores continuously improving. In the beginning, we didn't do that well, so that was our neural episode. And then by the end, we did actually really well. And in fact, by the end of the semifinals period, we were leading, so that's our system with the 3 stars. So we were leading in terms of the average user rating over the last 7 days. So then it shows 3 finalists, and Harriet Watt was one of these finalists, together with the University of Washington and the Czech Technical University. And as you can see from this graph, the 3 finalists did actually quite a bit better than all the other systems in terms of user ratings. So then by the end of the final period, again, we were rated on place 2, but as you can see from these averages, all the systems were pretty much as good as each other. And our system was indeed quite a bit better in terms of average length. So that was another thing Amazon really cared about, how engaged is the user during these conversations. So then to actually determine the final winner, our team was invited for the final show-off to go to Las Vegas. And it was sort of a funny coincidence that it was Las Vegas of all places, because the final evaluation was indeed a bit of a game of luck. So what happened was that we had 3 testers, and these 3 testers weren't experts as such. They were science fiction authors or radio DJs, and each of these testers had 2 conversations with our system, and then they were rated by external judges. Again, these external judges were non-experts again. And systems were asked questions such as, I want to talk about baseball, I want to talk about basketball. And unfortunately, when it came to our system, the user wanted to talk about highlight. So any idea what highlight could mean? No? You're very close, actually. You're very close. It's indeed a foreign language, which the user spoke here at this moment. But what our system made out of it is that it thought, oh, the best I can do is maybe pick up on the hi, and it said, hi, how are you? And then immediately the judges pressed the button and said, that's not a good answer, right? So what hi-li actually is, chai-li, it's written. And indeed, it's not English. It's a Basque word, and it's a game which is still played. However, the problem was that the Amazon speech recognizer expected the user really to stick to English and not suddenly switch to Basque, so it just couldn't recognize this. And unfortunately, we didn't have any control over the speech recognition, so this was done by Amazon, and we just got the results. So annoyingly, when you type to our system, it very well actually recognizes what this chai-li actually means, and it gives quite a nice answer by explaining to you a little bit of the background. So as you can imagine, this caused quite a bit of sour grapes at the side of our team. We still were very happy with reaching the 3rd place, and the lessons learned were that evaluation standards really define the game. So evaluation is a very important topic for us all to work on. And another lesson was that learning from big data is only valid in restricted contexts. Otherwise, you'll have your system telling you very inappropriate things. And then finally, the main takeaway message for us was really that getting lots of real customer data is really worth the effort. So in the end, we got over 360,000 rated customer interactions. So it should just give you an idea, we usually, when we evaluate our systems, if we're lucky, we get a few hundred. And these are not real customers, but we painstakingly invite users into our labs, which are usually, paid students, and hope that they, do a good job in interacting with our systems, give us a few ratings, or we post these jobs on, Amazon Mechanical Turk, so we crowdsource them, and then we get a lot of noisy data back. So to have a data set which is actually from real customers, which really want to use the system and have a goal using the system, is something very, very rare for university. And this type of data is really precious for us. So in fact, it's so precious that we do it all over again. And we are in the Amazon Challenge this year, so we are one of 8 universities this year, which was selected to participate. And we are currently doing really well, so we are on rank number 1 here. We are leading the leaderboard. This was just from last night, from yesterday. And if you want to know how we are doing in the rest of the competition, please follow our Alana bot. That's what our system is called. And if you want to get a feeling what Alana can do, it's installed on the Pepper robot outside. So please feel free to go and talk to it at the end of this lecture. So what are the remaining challenges, really? So I've already mentioned quite a lot of challenges, and there are even more to come. So this is a really promising field of research. You never run short of research proposals to write. So before I start this part of this talk, I want to warn you that this might contain examples which some of you might find disturbing. And just by putting up this slide, I can see that people are waking up, so that's great. Right, so what I want to talk about is ethical issues concerning these systems, and especially the first one, which is very much an issue with machine learning in general, is when you learn from biased data sets. So one thing which happened in 2015 was that Google, using machine learning techniques, Google Photos, actually mislabeled a black person as a gorilla, and that hit the press really badly, as you can imagine. There was a similar incident using machine learning techniques where it learned that if you have a black skin color, you'll be more likely to re-offend than if you have like lighter skin color. And on top of being racist, these vision systems are also sexist. So if they see a person in a kitchen setting, they immediately predict that this person has to be a woman, right? So it would mislabel this man as a woman just because he stands in a kitchen. So that's what we call bias in machine learning. And it's just regurgitating the biases which are present in the data. And this is not only a problem for computer vision, but it's also a problem for conversational AI. So in 2016, Microsoft released a bot called Tay. And this bot was supposed to learn from user tweets. And after a few hours, it actually became really racist and sexist. And in the end, it actually told the users why it did what it did. It said, I learned from you and you're dumb too. So what it basically said is, if you feed rubbish into a machine learning technique, you will get rubbish out, right? As simple as that. So I wanted to try that for myself. I particularly wanted to know what these new neural methods would make about sexism and bias in the data. So I asked a re-implementation of a neural conversational model. So this was a very famous paper released by Google in 2015. And someone went through the trouble to re-implement it and put a version online. And I asked the system about women and ladies, and you can read for yourself what it answered. So obviously there is bias in the data for these systems as well. So one obvious question is, does machine learning from data introduce biases for these conversational systems? So the other issue which we discovered was that actually 4% of customer conversations with our Alexa bot contain sexual harassment. And we think that's due because, Alexa, first of all, it's a female name. She has a nice female voice. She helps you. She does everything you say. So this invites abuse and general harassment. So obviously we are not too worried about Alexa's feelings, but what we are worried about is that if the system is not reacting appropriately, this user behavior might be reinforced, right? And there are indeed recent headlines, where parents are worried that Alexa condition their kids to be rude. And only a few days ago, these very colorful Amazon dots came out, which are specifically designed for children. So it's definitely, in the kids are one of the target groups here. So, what just happened? Okay, good. So in addition to the first question, we need to ask ourselves, how do current systems behave when faced with abuse? And what are good mitigation strategies to prevent this type of abuse? So we classified our 4% of abusive interactions into 4 categories. So they roughly fall into categories such as gender and sexuality, sexualized comments, sexualized insults, and sexual requests. So this is based on the definitions given by the Linguistic Society of America. And then what we did, we collected this data from our Amazon customers, and we went and used this data to insult a lot of bots. So we insulted commercial bots, rule-based bots, current data-driven ones, and we also introduced a negative baseline. So we insulted so-called adult-only bots. So those are sex bots on the internet, which I can reassure you we got the ethical approval of the university to do that. So what we found is that, not surprisingly, the adult-only bots were quite flirtatious. However, they were also chastising the user, and they retaliated the abuse. So they actually did push back, which was really interesting. The data-driven ones mainly didn't make sense. There were also some of the answers you could interpret as quite flirtatious, and they were also swearing back, just because of the statistical nature of the system. If you swear, if the input is a swear word, you're more likely to have a swear word in your output. Whereas the commercial systems mainly avoided to answer, so they avoided the whole issue. So our next question was, can we actually make these machine learning systems any better? So with respect to the first question about bias in the data, we thought, what would happen if we trained on a clean data set which didn't have any bias in it? So we got a data set like that from an industrial partner called Trio.ai. So this was, for example, filtered for profanities. However, the system was still quite encouraging and flirting back. So even though it didn't really have any profanities in its output. So the remaining question, one of the big remaining questions of my research is, what are good mitigation strategies? And as you can imagine, this is the most difficult question to answer. And I currently have two very talented PhD students working on this question. So I hope to update you in the near future of how to actually handle this type of abuse. So to conclude, in this talk, I've presented you with the idea of using machine learning methods for automatically building these conversational AI systems. And I discussed some of the advantages and some of the disadvantages of using these machine learning techniques. And for task-based systems, we said that these, especially these very current new neural methods produce very natural sounding output, but also output which is actually quite often incorrect. And then if you move to the more challenging task of open domain systems, or also called chatbots, we found that neural methods are really hard to control. And this is especially important if you deal with so-called edge cases. So cases where, the user starts abusing the system. So that's where you really want to have a system which you can control over what it's saying. So to conclude, I want to thank my amazing team who has helped me doing all this research. I also want to thank my sponsors for giving me money to do all this research. I want to thank my husband for supporting me to be able to do all this research. And if you want to know more about my research, please refer to my webpage where I've got most of my papers online. And if you want to know even more, you can sign up for our postgraduate program in conversational AI. So we teach a whole MSc on that. And this year, brand new, we've got a 2-year conversion program. So for those of you who are now really excited about AI, but don't have any programming or any computer science background, this might be the course for you. So you don't need to know how to program to enter, and we also have 12 fully funded scholarships to enter this course. And if you want to know more, there's a flyer outside how to apply for these scholarships. And please do stay in touch if you're interested in this research. So here's how to reach me. Thank you very much.